So, in scenario 1, you got a copper sphere with a specific heat capacity of 386, whose mass is 400 grams. Submerged in liquid nitrogen, whose temperature is negative 180. When the sphere is removed, it's then immediately transferred to an insulated aluminum container of mass 500, whose specific heat is 900. The container has what? The container has water. Okay. And temperature of the water in the aluminum container is 10 Celsius, right? So which one is the hotter object? The copper or the aluminum slash water? Yep. Temperature-wise, they're higher because they are at 10 Celsius versus negative 180 Celsius. Okay. And so when you put them together, there's going to be something called heat transfer, and they're going to transfer heat until they become the same heat at some point. So what we do is we say negative Q by the hotter object is equal to Q by the colder object. And the hotter object is going to be the aluminum and the water, right? So we're going to say negative MC delta T for the water. So the mass of the water is 900. The C of the water is 4186. And I'm just going to say here delta T because they, actually, no, I'll say TF minus how much the water was at. The water was at 10. Plus the mass of the aluminum, which is 500. C of the aluminum, which is 900. Times aluminum was at 10 as well. Okay. This thing here is equal to the Q of the colder object, which is the Q of the copper. So MC delta T for the copper. The mass of the copper is how much? It's 400. The C of the water is 386 times TF minus the copper was initially at negative 180. Yeah. All right, so now it's time to do some math. Let's take care of the top part at least. So look, there is one thing we gotta be careful here with, is that the C is given to us in kilogram, but the mass given to us in grams. So convert every gram you have into a kilogram. So like this becomes 0.9. This becomes 0.5. And this becomes 0.4. Now I'll do the math. So here we got minus 6.4.
I got a very large number. Yeah.
You're on the right track?
Yep.
Let's see. Plus, this becomes plus. We're looking for the TF. TF here, TF here. And let's just now combine all the TFs. So I'm going to remove the minus sign here. So minus this becomes plus. Minus this becomes plus.
What?
Yeah, because there's a minus on the outside. I applied it to all of them.
Okay.
Assuming I'm right. So I put all the TFs on one side. I got negative 4371 TF is equal to negative 14,378. TF is equal to I got 3.28 or 3.3 Celsius. 3.28 will do. Very good.
Are they strict about significant figures in physics?
Just if you're unsure, just put 2. If you're unsure. Okay. Now that was part A, right? The insulation from the aluminum container is now removed. The temperature of the air in the room is greater than the final equilibrium temperature of the copper, water, and aluminum container. Sketch a graph of the rate of energy transfer as a function of time through the walls of the aluminum container. A positive rate of energy transfer means from the interior to the exterior. Negative means from the exterior to the interior. So look, now the temperature of the air in the room is more than the temperature of the copper, water, and the aluminum container. Which means that the heat has to be moving from the air to the aluminum, right?
Yeah.
Negative rate of energy transfer moving from the exterior, which is the air, to the interior. So look, basically we're gonna go with the negative because the heat will travel from the air to the aluminum.
Yeah.
So we're gonna have to start here. And of course the heat will keep getting transferred until at some point there's no more heat transfer because we're gonna have what we call thermal equilibrium. So basically we're gonna be starting somewhere here, we're gonna be ending somewhere close to a 0. Something like that will do.
Why?
Well, as we transfer heat, at some point they must have the same temperature. At some point there is no more transfers of heat. That's why it's going to be approaching 0 over time. And it's negative because heat's getting transferred from the outside to the inside.
Okay.
Yeah. In scenario 2, the entire process of scenario 1 is repeated with all the following changes. Now, the aluminum is going to have more water than scenario 1. Insulation has been removed from the aluminum container. Okay. So C indicate whether the final temperature of the system consisting of the water, copper sphere, and aluminum container will be greater than before, less than before, or the same as before. Let's take a look at before. Who was transferring heat to who? It was aluminum / water transferring heat to the copper, right?
Yeah.
Because they were simply hotter than the copper. But now we have put more water than before, right? Now what they do? They put more water than before. So now the container of the aluminum of the water simply has more heat in it, okay? So more energy is going to be transferred to the copper. And also the insulation has been removed. That means more heat can also be transferred. So 2 reasons why we're going to choose greater than before. Okay. 2 reasons. Why? Because now the aluminum / water container has more water, so more energy is contained in it to be transferred to the copper, and because the aluminum insulation has been removed, so more energy can leave the aluminum water container. So greater than. Okay. Now, that was, I guess now, okay. We got two charged spheres, each with a charge of plus q, are held on the in a place on the x-axis at negative a and x is equal to a. We're going to be releasing a small charge object with a charge of negative q from rest on the y-axis. The bar charts in figure 2 represent the electrical potential energy of the sphere object system and the kinetic energy of the small charged object when the object is at positions plus y, 0, and minus y. And they only gave us the one at plus a, correct? Okay. In figure 2, draw bars to represent approximate values of u and k when the charged object is at position of y is equal 0 and y is equal to minus a. Okay. So let's just check how they're similar or different from each other. Plus a, y is equal to plus a. We have y is equal 0.
And minus.
Y is equal to minus a. So u is negative at y is equal to plus a, but k is 0. So y is equal to plus a. The u is negative, but the k is 0. Okay. Of the sphere's object system. The k of the small charged object. Right, so the u is for the entire system, and the k is only for the small charged object. And why is the k 0 at position plus a? Do you know why? Because I guess it's because it has not moved yet.
Oh, yeah.
That's why. It just, we just started there.
So it's at rest.
It's at rest at the moment. Yeah, exactly. Now we're going to have to represent it at y is equal 0. And then we're going to have to present it at y is equal to minus a. So look, let's assess the u at position plus a to understand why it is currently negative. So we're going to say, now look, u is equal to k q1, q2 over r. So we're going to do plus q on the minus q. Then we're going to do the other plus q on the minus q. So k q1 q2 over r. And how far are the two charges from each other? They're far by the hypotenuse, correct?
Yeah.
So the hypotenuse is going to be basically equal to the combination. So it's going to be the root of a squared plus a squared, which means the root of, so a the root of 2. Okay, so we're going to put here a the root of 2. So we're going to stay, instead of this one, where is it? 1 second. Yeah, a root of 2. So we're going to put here a root of 2. Okay. And that's by this charge. Now how about the second one? It's the same thing, right? It's also equally distant, right? So we're going to just add it up. So we're going to have k, q, minus q over a root 2. So we're going to have a root 2, negative 2k, q capital. And as you can see, it is negative, right? The u is negative. That's why it's going to be under the x-axis. How about the u at the y of 0? So when the y is equal 0, let's see how much that is. Now again, the charges will be equally distant, right?
Yes.
Now they're going to be... So here we're going to have this and this. So we're going to have k, q, negative q over r, which is just an a, plus k, q, negative q over another a. So a, 2, negative 2, k, q, q. Which one is larger, now or then?
What do you mean now or then?
So this is then, and this is now. Which one is larger?
Then?
Then, because right now, this just means negative root 2 times k, q, q over a. But then, now it means negative 2. So negative root of 2 is like a negative 1.4, but now it became negative 2. So come here and make your u bigger than before and, negative, right?
Yes. They just said it's positive, nothing else?
Well, look, k is this energy of motion, correct?
Yes.
Okay. So, and now it would be moving, right? So it has to be moving from here to here. So if it's moving, it has to have a specific value of k, right? Which is positive. And is it going to be the same as the original? No. Because essentially, look, you're starting from here. That means the combination of this one and this one have to add up to get us back this one. So let's just imagine that this is a negative 5. So if that is, let's say, a negative 8, this one has to be a plus 3, right? For the whole thing to be.
Yeah.
Or if we want to go further than that, which I don't think it's needed, but let's just say we go further than that. You know how we did here root of 2, negative root of 2?
Mm-hmm.
So if negative root of 2, which is 1.4, is equal to 1 tick, how about a negative 2? So right now, if you divide 2 by 1.4, that would be 1.4 ticks. Okay? And so, just the k and the u have to add up to get back to this value here. Negative 5, let's say. Negative 8 plus 3. Now, we're going to go all the way to negative 8, right? So look, what I've noticed is when you're beginning, you must have a 0 k. But how about when you end? It all depends on the u. Let's find the u here. And by the way, the u here at negative a is the same exact u at positive a, right? They're just mirror images of each other, the same exact distance. That means we can go back to our original u of this bar. And so you can only have minus 5. That means k has to be 0. So the endpoints have to be the same as each other, essentially. Okay. Part B. derive an expression for the speed of the small charged object when it reaches y is equal 0 in terms of whatever, physical constants, when it reaches y is equal to 0. So look, originally we started at y is equal to plus a, and I told you already that the u is equal to negative root of 2 k q q over a, if I'm not mistaken.
It's not root.
Yeah, it is, because 2 over root of 2. Okay. That was where we started. And then at y of 0, the u became larger, became negative 2 k q over a, and plus some k e. And of course, because of the conservation of energy, what we have at plus a is the same what we have at 0. So I'm going to say negative 2 k q over a is equal to negative, sorry, this is root of 2, is equal to negative 2 k q over a plus ke. So k is equal to, move these to the other side. So we're going to have a here, negative 2 root k q plus 2 k q. Now, what's the equation for ke? Because we want to derive an expression for the speed, right? So I'm just going to say k is equal to half mv squared. And so v is equal to m times a. We're going to move that. We're going to square everything, obviously. Move that 2 there. And I guess I can factor out the k q negative root 2 plus 2. Now I guess I could do that. Yeah, I got it, basically, so we are good. And, if you actually simplify it further, you can just, add negative root of 2 plus 2, which will give you, no, it's the same, doesn't matter. Okay, leave it like this. We got it. Okay, now see on the axis in figure 3, which is, okay, figure 3, oh, this one, okay. Sketch a graph with the KE. Okay. So we're supposed to be sketching basically the K as we go from negative A to A. Now, as you know, we already know that at the endpoints, there is a 0 K. But then in the middle, there's a full K, right? It's the highest K possible in the middle. So that means it's going to be 0 here and 0 here, but some value here in the origin. Okay. The charge of the small charged objects changed now to negative 2q. And the object is again released from rest at y plus a. Describe how one feature of the graph you drew in figure 2 will be different.
1 second, I don't think like that.
Oh. So look, let's just go back to how we found the k. K was equal to u at point plus a minus u at, wait. So the equation was u at plus a was equal to u origin plus the k at the origin, correct?
Yes.
So u plus a minus u origin is equal to k origin. Now, the U plus A, if you recall, was basically negative root 2K Q over A minus U at the origin, which was 2K Q over A. Okay, so right now if I factor everything, if I factor the K Q over A out, I will get negative root 2 minus root 2. So it does, yeah.
What are we doing exactly?
What are we, wait, so, yeah, negative. Oh, it's so positive, I mean. Because basically, look, we're doing negative or minus, it's already a negative. So minus 2K Q over A. It becomes positive. So I'm going to have negative root 2 plus. Okay, so now I can factor out the K Q over A minus root 2 plus 2. Yeah? Okay. And so it does seem like that the smaller q does play a role. So now if I were to make it double what it was before, then of course the peak would be higher than before, correct? And so the peak would be now greater. So maybe it's going to be like this instead. So the peak gets higher. Okay. Since the K is direct with the smaller q. Okay. Question 3. In experiment 1, students are asked to determine experimental value for Wien's constant, which appears in the equation lambda max is equal to B over temperature. The students have access to a bulb that approximates the spectral output of a black body and a sensor that can record the intensity of the light emitted by the bulb as a function of wavelength. The temperature of the bulb can be varied, and the students have access to a sensor that can measure the temperature of the bulb. Okay. So describe a procedure that will allow the students to use a graph to determine the Wien's constant. Provide details that students can replicate, including any steps. So look, they did mention that we have access to a sensor for the light intensity, and that we have a sensor for the temperature. And the temperature can be varied. That means that temperature is going to be your independent variable. Temperature of who? Of the bulb. So now what we're going to say is the following. Okay, for a certain temperature value as recorded by the temperature sensor, bulb temperature value. Okay. They have access to a bulb that approximates spectral output of black body. So basically use the okay, so for a certain bulb temperature, right? You're gonna get different bulb intensity, basically. So you're gonna have to use the intensity of the bulb. Okay.
So for every temperature, we get a different intensity.
Exactly. Okay. Versus the wavelength. data. So you're going to be plotting density versus wavelength data, right? In the attempt of finding the maximum wavelength. Okay. To find the Y max. Okay, and repeat this procedure using 5 different temperatures. Yeah. So each temperature gives you a different lambda max. Yeah. Okay.
Now it makes some sense.
A bit, yeah. Okay. Now, part B, describe how the collected data could be graphed and how that graph would be analyzed. So look, you are changing the temperature, correct? Temperature has to go on the x-axis.
Yes.
And so we're going to say plot lambda max as a function of 1 over temperature, because temperature is going to be on the x-axis. And so it's like saying y is equal to mx. Y is the lambda max, m is the slope, which is b, and the x is the 1 over t, basically. So the slope is b, which is the Wien's constant. Yeah. Okay. And you expect, of course, a linear graph. Okay. In experiment 2, the students have a glass vacuum chamber with 2 parallel metal plates inside. So this one and this one. As shown, the students are asked to use the setup to determine the work function of the metal plates. In each trial, the students use a monochromatic light, which means a single wavelength source, to shine light on one of the plates. Once current is detected, the students will increase the potential difference of the power supply until the emitter reads 0. They collect the following data when the current stops.
Relate to this.
So you want to determine the work function, which is the minimum amount of energy required to release an electron. Yeah. And
I'm
work
so confused right now.
function. You are so confused
Yes.
right now. Okay, why don't we just look at the equation required, right?
Sure.
So when discussing the work function, you must discuss this equation. K is equal to HF minus the work function. Okay.
Oh, now it makes sense.
And K is measured in joules, right?
Yeah.
K is measured in joules or in EV. They're both correct. Now, so instead of K, I can put Q delta V, because that's actually in the equation sheet. Well, actually it's U, but U is the same thing as K most of the time for the equations. So now I'm going to just say K is equal to Q delta V. So Q delta V is equal to HF minus the work function. Now, here we're discussing work function of the metal. Yeah, So now I want to isolate delta V. That means I must divide everything by Q. So I'm going to have HF over Q minus the work function over Q. Okay. And now what we're trying to do is you want to find a straight line to find the work function, right? And so if we were to implement y is equal to mx plus b, and we are able to vary the f, okay, we're able to vary the f because they said different wavelength, that means different f. So that means our y-axis is delta v, our x-axis is the f, our slope is h over q, our y-intercept is negative work function over q. So now the vertical axis is the y-axis, which is delta v, any change in voltage.
Yes.
Horizontal axis is going to be the frequency. So use the blank columns in the table to list any calculated values. Well, yeah, I mean, we should now calculate the f, right? So I'm going to calculate the f. So how would we calculate the f? By doing f is equal c over lambda. So we're going to apply the c over the lambda in meters for all of the rows. We have 4 rows, we must apply it 4 different times. Sorry, the speed of light is positive. First one I got 6.7 times 10 to the power of 14. Of course, the unit has to be hertz. Okay, next row.
I got 8.5.
8.5.
Times 10 to the power.
Yeah, 8.5 times 10 to the power of 14 again. And then 1.2 times 10 to the power of 15. And then 2 power of 15. Okay, so now I have a dilemma here because I have different powers. So I'm gonna either make all of them power 14 or make all of them power 15. Okay. So it's obviously a preference. It's your choice. Which one do you want?
Which one is easier to do?
In my opinion, you make all of them power 14. That means I'll make this power 14, but if I do, I must remove the point. So it's going to be 12 times and then power 14.
Yes.
And same here, 20 and then power 14. So we just have an increasing number from 6.7 all the way to a 20. Okay. Very good. Now it's time to actually graph. Exactly. We're going to be graphing, I think. So let me just type paste this. Okay, so I'm going to be labeling my y-axis with delta V. And of course the volt is the unit. And my x-axis with F, which is the hertz. Now, my delta V has to range from 0.45 to 6. So I guess I could start off with, I must end with 6, right? I can end with 6 in the end. 6, 4, 2, 0, -2, -4. Okay. Actually, no, that doesn't make, why would we have a negative voltage, right? Actually, wait a minute. Oh, I can tell why. Because see how the y-intercept has to be negative? That means we actually have to go under the x-axis, so keep it as negative.
Okay.
Yeah. F will be times 10 to the power of 14, and it has to be ranging.
Well, you better get paid for it.
Oh yeah, I did. So look, from 6.7 to 20. So I guess I could do 5, 10, 15,
And
20. No. So 6.7 for the frequency with delta V of 0.45. So 6.7, which is here, with 0.45, which is 45. Wait, so this is 0.4, 0.8, 0.5 is here, so they're gonna meet up here. Okay, now we're gonna do 1.25 with 8.5. So 1.25. So that's 1.25 with 8.5, which is here. Then they will do 2.65 with 12.65. So it's going to be here with 12, which is here. Then we're going to do 6 with 20. So 6 with 20. Okay. Now, of course, now I must do a best fit line. That has to go through, like, try to be accurate.
This one's pretty accurate.
Yeah, let me try again. I think that's the best. That's pretty close. And the y-intercept is going to be hitting it at -2, right? And the y-intercept we just found out earlier to be negative work function over q. That's the y-intercept. That's why it's negative. It's under the x-axis. And so, yeah.
So now we calculate.
The y-intercept. We calculate this up?
So using the best fit line, calculate an experiment.
Right, so we're going to say -2 is equal to negative work function over the q. The q is just the charge of an electron, right? 1.6 times 10 to the power of -19. And so the -2 is in volts. The charge is in coulombs. So then if you multiply charge by coulomb, you get, if you multiply voltage by coulomb, you get EV, electron volt. So -3.2, positive, yeah. That's going to be the work function. Yep. I think it is. Or just, so joules, yeah. And suppose they want it in the electron volts, you can just divide it by 1.6 times 10 to the power of -19, and you get 2 electron volts. So they didn't ask in which unit, so you can report it either in joules or electron volts. They're both going to be correct. Okay. A circuit has a battery of EMF, a resistor, a variable resistor, and a capacitor. The variable one is more than the fixed one. And if they say steady state, do you know what that means?
It means it's steady.
Wow. Okay, that means the capacitor is fully charged.
Yes.
That means no current will go through the capacitor branch, and all the current will have to simply go like this.
Avoid the C.
Avoid the C, exactly. Now, the charge on the capacitor is going to be Q1 when it's fully charged. Okay. And Q0 or QO is when the circuit is connected for a long time. Okay.
So after a while it will be Q0.
No, in the beginning it's yeah, like Q0. Oh, wait, so in the beginning, RV is equal to R, it's Q0. But then RV becomes more than R and becomes Q1. So look, when the RV is equal to R, it's Q0. When the RV is bigger than R, it is Q1. So part A says indicate if Q1 is greater than, less than, or the same as QO. Justify your answer.
Without manipulating equations.
So look, when the RV is equal to R, okay, they will get the same voltage as each other. So EMF in the V is going to be EMF, EMF of the RV is equal to EMF of the R. But when RV is bigger, it will receive more current. It will receive more voltage.
Yes.
Okay. Because ultimately, voltage is equal to I times R, and both R's are going to be in series with each other. So whichever, they both get the same current. So whichever has more R gets more voltage. And as we know, the capacitor is going to be in parallel with the RV. And so if the voltage of the RV goes up, the voltage of the capacitor also goes up because the capacitor is in parallel with the RV. So it gets the same exact voltage as the RV. Now, since Q is equal CV, right? And so Q is going to be direct with V. So if the voltage of the capacitor goes up, the Q of the capacitor goes up as well. So ultimately, Q1 is going to be bigger than QO. So greater than. B. Derive an equation for the charge Q1 on one plate in terms of...
I'm not sure if I'm correct.
So wait. Let's just use Kirchhoff rule. Do you know what that is?
The loop rule and the junction rule.
Right. So it says that... Wait, are you asking me or?
No, I'm telling you what it is.
Okay, so it's saying that the EMF of the battery minus the EMF in each R should become 0 in the end.
Yes.
So minus I times R minus I times RV, the whole thing has to become equal to 0.
Yes.
Now we can simply move everything with the I to the other side. So I'm going to have EMF is equal to IR plus IRV. Take out the I, and now bring the R and the RV down. So now we have an equation for the I.
Yes.
Okay, now the voltage in the capacitor is equal to the voltage of the RV, correct? And the voltage of the RV is just equal to I times the RV. So the voltage of the capacitor is equal to, instead of I, put EMF R plus RV times RV. Now we know that Q is equal CV, voltage of the capacitor. So Q is equal C times EMF over R plus RV times RV. And that's about it. That's the equation. Okay. And then C says, does the equation you derived in part B agree with your claim in part A? The claim being Q1 is greater than the QO. Well, actually it does, because according to this equation, Q is going to be direct with the RV. And so if there is more RV, there is more Q. Okay. And And also it shows us how Q is going to be inverse with R plus RV. So of course, as the RV increases in the denominator, the Q will be well, actually, wait 1 second. So just going back for a second. So Q is going to be direct with RV over R plus RV. The R, the capital R, is not going to change, right? But the RV will change. And RV is by itself in the numerator. That means RV has a bigger impact when it's the numerator than the denominator. Because alone. So if the RV goes up, the Q also goes up. So yeah, it is going to be consistent. It does agree with the claim.